under handouts on Blackboard, you will see a file. I think it says something like hypothesis testing proportion examples. So if you'll print it out, I think there, I'm not really sure. I think there are 3 problems, maybe 4. Yeah, there are 3 problems. Okay. What I want to do, I want to work number 1 and number 3, just a standard p-value method. So number 1 and 3, I'm going to use the p-value approach. That's going to be the one you're mostly going to use. And number 2, I'm going to use the critical value approach, just to give you a demonstration of it. So it's a little harder. It takes more work. So let's see if we can get down where you guys can see this a little bit better. All right, perfect. Now, guys, in both these situations, we're going to use both of these approaches for all 3 problems. We're going to use the 4-step process. Again, what do? We set up our null and alternative hypotheses. We check the conditions for the test. We calculate the information for the sample data, and then we make our decision. So we're going to follow the same 4 steps that we used for hypothesis testing for population means. So a medical journal reports that 30% of patients who visited the ER in hospitals across the country are on public assistance. An administrator of a hospital in the Appalachian region would like to test this claim because she feels the percentage is higher at her hospital. Now, guys, what you're thinking there is that gives you an indication of what you're going to be testing, and it gives you an indication of what inequality you're going to use in H sub A. Okay? She checks the records from a random sample of 1,200. So right now, as I read things, I'm thinking things as I go along. First of all, there's a report about everyone. So I know that P is 30%, and I'm always going to want to work with the decimal part. I also know this higher, as I indicated earlier, but when I come on down, visited the ER and found that we have a random sample of 1,200, so I know my N is 1,200. 392 were on public assistance. So from this information right here, I know that P hat, which we can find by taking X over N. Let me grab the calculator. Is 392 over 1,200. So 392 divided by 1,200 gives us 0.32666666. So I'm going to go out 4 places. So 32.7% of our sample were on public assistance. Now we want to test if it's higher. And again, someone that knows squat nothing about statistics will say, well, this is a bigger number than what we currently believe or what's stated about all hospitals. So done deal. Guys, that's not the way it works. We have to let the process be carried out. Just because this is higher doesn't mean it's enough higher to reject this claim. So we got to let it play out. So, guys, first thing I'd want to do is set up the null and alternative hypothesis. So it's so tempting there to put mu equal, but guys, this isn't a mean problem; it's a proportion problem, percentage problem. So 0.30. H sub A will always use the same letter and the same number with a competing inequality. And since the, let's see, who is this? The administrator wants to test higher, it should make sense that we are going to use a right-tail test, a one-tail test. Now, something I just noticed, I hesitated there because I noticed something. I said use the 5-step procedure. The additional step is to calculate the confidence interval. So if that was confusing, that's just the additional step. Okay, what's our alpha level? Looks like we're going at a 0.05 level of significance. Now, this is the first part, and this is the second part. Also in this part, we have to check the conditions of the problem. And it turns out that we need n times p and n times 1 minus p to both be greater than or equal to 5. So n in our case is 1200. P is 0.30. So guys, you can see that that's what, 360? So that's clearly greater than or equal to 5. And then n times 1 minus p is going to be 1200 times 1 minus p, be 0.70. So clearly it's greater than or equal to 5 too. So we can check off the second part, which is the condition and the assumptions to run the test. Now, what would happen if one of these isn't? Because again, both of them have to be. If one of them isn't bigger than 5, then you can't really run the test. I mean, you can run it, but the results aren't believable. So what you would need to do, and guys, I need to make this a little clearer. What you would need to do is you just need to bump up your sample size. Go out, and instead of taking 1,200 hospitals, you need to take 2,000 hospitals. Okay, let's get to the test. Now, what we're going to do here is we need to calculate the test statistic. And for reasons that I explained in the previous video, the test statistic is going to be a z-statistic. And since we're working this using the p-value approach, we need to calculate the p-value. All right, so guys, easy to do. Go to StatCrunch. Let's go to Stat. Let's go to Prop Test. We'll go to one sample, and we have Summary. So the number of successes. Now, guys, a success in the context of this problem is our x. Well, the number of successes is always x, but in the context of this problem, it's actually being on public assistance. So we found that 392 of the sample was on public assistance. There was a total sample size of 1,200. We want to test 0.30, and we want to test greater than. Okay, we don't need to store anything. We don't need a p-value plot. Let's just compute. Now guys, when we get our output here, we got a lot of stuff going on. First of all, we've got our x under count, our n under total. This is our p-hat, the sample proportion. There's the standard error. And then at the end, we've got what we need. We have our z-statistic, which is 2.016. And our p-value is 0.0219. All right, so I wrote those there. Now the next step is to make our decision, and remember, to make our decision, we compare our p-value with our alpha. So guys, our p-value is less than our alpha, which tells us we need to reject the null. So by rejecting the null, now we typically don't get this this dramatic, but rejecting the null, and you don't get so dramatic that you draw a line through it. But again, rejecting the null says that the alternative statement is more believable than is the null hypothesis. So right now we're believing that the hospital administrator is onto something, and the information from this study does indicate that there's sufficient evidence to conclude that the percentage of ER patients in her hospital is higher than what they found for hospitals across the country. Now, the fifth thing that you would maybe want to do is calculate a confidence interval, because think what we know right now. We know right now that P is greater than 0.30. At least that's what we're led to believe from the test. There's a lot of numbers bigger than 0.30. 0.31, 0.32, 0.97, a lot of numbers. The confidence interval is going to allow us to tap into a better estimate. So what we could do is go back to StatCrunch, go to PropStat 1 with summary, type the information back in. I think it was 392. Is that right? Yeah. Observations 1200. And instead of calculating the hypothesis test for P, we're going to do the confidence interval for P. Okay? So we're going to compute. So it looks like the lower limit is 30.0%, just barely above that, up to 35.3%. So I wrote that down over here. So, you know, even though 30% was being tested, and the way I've rounded this, it turns out to be the same value. This was actually a little bit above, therefore we got the statistical significance. So it appears that the percentage of patients in this region, in the Appalachian region, based on the results of this study, is slightly higher than 30%, somewhere between 30% and about 35.3%. Now, okay, I'm getting more distractions. My wife just texted with a question. Now, this question I want to do using the critical value approach, okay? But it's going to set up the same. So, a political expert claims that 60% of Americans believe government regulation of businesses does more harm than good. Well, I know right there that my P is 60%, but I need to work with the decimal equivalent of that at 0.60. You wish to test the claim. When I see that, I think it doesn't say test because I think it's higher, doesn't say test because I think it's lower, just says wish we test the claim. So we use the generic not equal to. Select a random sample of 762 and ask them if they believe about if government regulation does more harm than good. 1,004 said yes. So P hat is 1,004 out of 1,762. Which is 59 or 57.0%. So I'm just going to put 5698, right? Yeah. Now, alpha level 0.05. Let's do this problem using the critical value approach instead of the p-value approach. Okay, guys. Same thing. Start out with the null hypothesis. Again, it's so tempting to put a mu there because that's what we've been studying, but these are percentage problems. So we use a p. H sub a, guys, remember, whatever's there always comes down here. Less than, greater than, not equal to, well, the problem sets up as a not equal to. Alpha equal 0.05. We know from this that we're going to conduct a two-tail test. All right? Number two, I'm going to go ahead. I can do this in my head. I know that 0.6 times 1762 is bigger than 5. I know that 0.4 times 1762 is greater than 5, so my conditions are satisfied. I'm just going to put down that alpha is 0.05 here and say conditions satisfied. All right. Now we're going to use the critical value approach. So the critical value approach, because we're testing a not equal to in the alternative hypothesis, we're going to see that the distribution of sample proportions is going to use the z distribution with mean 0, standard deviation 1. Because I'm testing not equal to, I'm going to have two tails of rejection. And the total area in these tails has to equal my total alpha. So guys, down here I have to have half of 0.05, and up here I have to have the other half of 0.05. So in here I'm going to have the remaining part, which is 95%. I also know that this is going to be the negative value and this is going to be the positive value. The absolute value of these numbers will be the same. So if this is negative, well, I can already tell you it's going to be negative 1.96. But if this was negative 2, that's going to be positive 2. If this is negative 3, that's going to be positive 3. So let's go see why. I just told you what the answer is. Let's go see why it's negative 1.96 and positive 1.96. So, guys, we don't use the t-distribution here, right? We use the z-distribution, the normal distribution, mean 0, standard deviation 1. And I think the easiest way to do this is just do between. And I want the area between to be 0.95. And I can see that the left bound and the right bound, which are critical values, are negative 1.96 and positive 1.96. Now, what I need to do next is I need to see where my critical, or where my test statistic. Where does it fall? If it falls between negative 1.96 and positive 1.96, it means I fall in this area, which is fail to reject. If it falls down in one of these tails higher than 1.96 or less than negative 1.96, well, we fall in the rejection region. So let's go calculate it. So guys, the test statistic is z. It's p hat minus p over the square root of p times 1 minus p over n. So our p hat, we found that, we didn't find that, did we? Yeah, we did. Our p hat's right there, 0.1004 over 1762, so it's 0.5698. Minus p, that's what we're testing, 0.60. Over the square root of p times 1 minus p over the sample size, which is 1762. All right, so if we can put that in our calculator without doing something goofy. So I want to make sure that the numerator is in parentheses. And then I want to take the square root of 0.6 times 0.4 divided by 1762. So our test statistic is negative 2.59. Right? So when I go back to my drawing, I see the negative 2.59 falls down here someplace, doesn't it? So what area do I fall in? I fall in the reject H sub O area. Next step, probably would, I would interpret, well, actually, this is the fourth step right here. The fifth step, I would calculate the confidence interval to locate. So the confidence interval, proportion, one sample with summary. So again, I have 1004 out of 1762. Confidence level 0.95, compute. So we're 0.547. Guys, I want to write this down. So 54.7% to 59.3%. All right, so I just wrote that up here. So instead of being 60%, it actually feels like people aren't quite as cynical, or at least have a little bit more faith. So it seems like a lower percentage feels that regulations of businesses does more harm than good. So I don't know. You interpret that however you want to. All right, let's go back to this problem. Let's do the p-value approach. So according to Nielsen Media Research, of all U.S. households that owned at least one television set, 83%, guys, that tells me right there that P is 83%, which is always worked with as its decimal equivalent. A local company, cable company, canvassing the town to promote a new cable service, found that of the 300 randomly selected, 240 had two or more televisions. Significance level 0.05. Is there statistical evidence to conclude that the percentage of households owning at least one television set is lower? So that tells me my alternative hypothesis is going to be less than. All right, let's do it. H sub O, P, 0.83, P less than 0.83. Why less than? Because we want to see if it's lower. Second, alpha 0.05 n times P is 300 times P is 0.83. Clearly bigger than 5. It should be 0.17. Also bigger than 5. Don't believe me? 300 times 0.17 is 51. So 3. We'll use the p-value approach. So what we need here is our test statistic. And we need our p-value. All right, let's go get it. All right, stat, proportion stat, one sample with summary. Number of successes here were 240. Number of observations, 300. We want to test what, 83, 0.83, and they want to test lower than. All right, compute. So what we get here is we get a z statistic of negative 1.38. I'm going to write that down. We'll go back over there in just a second. And our p-value is 0.083. All right, so I wrote that down. What does that tell us? Well, our p-value is greater than our alpha. So we failed to reject H sub O. So guys, when you fail to reject, you have no reason to reject this statement, so it's more believable than the alternative. So P equal 0.83, 83% of TVs with, well, I should say 83% of the households who have TVs, 83% of those, okay, let me restate that. Of the households who has at least one TV, 83% have two or more. So fail to reject and just conclude that it appears that 83% is believable. Guys, let's calculate a confidence interval. The fifth thing we do. So again, 240 out of 300. Confidence interval, compute. So 75.5% up to 84.5%. Notice that our 83% is contained in this interval. But it doesn't always have to be that way. When you're testing less than or greater than, there's a region in your distribution of sample proportions where you get wacky results, where you actually get statistical significance and you reject the claim, but the value is in your confidence interval. But that didn't happen here. But remember, it will never happen when you test not equal to. Guys, that's all I got. Have a great day.